This lesson deals with series resonance. You can find these notes in the course ebook in Chapter 4, starting on page 23. In our last video, we did an example where Z equivalent was 50 minus J75 ohms at a frequency of 1000 radians per second. Doing this symbolically, you could think of this as some R equivalent. And because this is a negative sign, we could think of this as some C equivalent. In other words, where there's the impedance of the capacitor is minus J over omega C equivalent. We could solve for C equivalent in this case because that's equal to 75. Just cross multiplying here, we'd get C equivalent is 1 over 1000 and then 1 over 75, and that's 13.33 microfarads. Plus frequency is changing, the size of the impedance of a capacitor and the impedance of an inductor are going in opposite directions. In other words, as we increase frequency, the magnitude of the impedance of the capacitor decreases because we're dividing by omega. But for an inductance, it's J omega L, so the magnitude is omega L, and so it increases as omega increases. But they have opposite signs. Is there a point where they cancel each other? There is, and this is called the resonant frequency, where the input impedance of a circuit is purely real. Well, let's solve for the frequency where that happens. On our problem, we have a series combination of an R, a C, and an L. Write this as R minus J over omega C plus J omega L. Pull out the J, and I've got omega L, and I've got a minus 1 over omega C. For this to be purely real, this quantity has to be equal to 0. Setting this equal to 0, that means that omega L equals 1 over omega C. Bring that omega over here, you get omega squared. Bring the L over here, you get 1 over LC. Take the square root of both sides of the equation, and you get 1 over square root of LC. We're going to call this a special frequency omega naught. Divided by 2 pi, and we'll get that in hertz. But the frequency 1 over 2 pi squared LC, the impedance of our circuit, is equal to just a purely real value. Series resonance has some interesting properties. Let me do an example. Suppose I take the wall outlet, which is about 170 degrees at 60 hertz, so it'll be the cosine of 2 pi 60 times t, my voltage. I have a resistance here of 10 ohms and a capacitance of 10 microfarads. What value of inductance would bring this circuit to resonance? Then finding that value Val, can you solve for the current I of S, V sub L, V sub C, and the voltage across the series combination V sub LC as a function of time in steady state? As we showed on the last page, the resonant frequency, omega naught, is equal to 1 over square root of LC. Well, I know the frequency is 60 hertz. I know the value of C is 10 microfarads, so I can solve for L. Square both sides of the equation, and then bring the L over here, bring this over here as a square, and the 10 microfarads. This turned out to be 703.62 millihenries. I'm going to stick that in for that inductance. Let's use our three-step algorithm to find the current and the voltages in the time domain. Step 1 is to convert our circuit to the frequency domain. Our frequency is 2 pi 60, which is 377 radians per second. Our voltage source is 170 at angle 0. The resistor is still a 10 ohm resistor. The inductance is J omega L. That gives me a plus J 265.3 ohms. The capacitance has an impedance of minus J over omega C. 377 times 10 microfarads, reciprocal, is a minus J 265.3. Same value, but the opposite sign. Let's see what effect that has. The current I sub S is the voltage divided by the total impedance looking into the circuit. 170 at angle 0 divided by the sum of these three impedances of 10 plus J 265.3 and then minus J 265.3. And these cancel, leaving me with just 10. So I get 17 amps at angle 0. Now that current flows in this capacitor and creates a drop of 17 at angle 0 times the impedance. Let's put this into polar form. The minus J is on the border of the third and fourth quadrant, so it's a minus 90 degrees, and the magnitude is 265.3. The product of these two magnitudes is 4,510, and the angle is minus 90 degrees. The voltage across the inductance is going to be 17 at angle 0 times the impedance of plus J 265.3. This is on the border of the first and second quadrant, so it's a 90 degree angle. Magnitude is 265.3. Multiplying these two, I get 4,510 at angle plus 90. Now let's find the voltage V sub LC. The rise in voltage equals the drops around the loop. Let's convert this back into rectangular form because we're going to be adding stuff. This is going to be 4510 with a plus J. This is going to be 4510 with a minus J. But these two are equal and opposite, and they cancel and we get 0 volts. The voltage across here is 0, but the voltage across here is not. It's a magnitude of 4,510, and this has the same magnitude, but the opposite angle. So they cancel each other. Step 3 is to convert back into the time domain. It's 17 at angle 0. That becomes 17 times the cosine of omega t plus 0 amps. The voltage across the capacitor was 4510. That's 4.51 K. Cosine of omega t minus 90 degrees volts. Voltage across the inductor, 4.51 K. Cosine of omega t plus 90 degrees volts. And then lastly, the sum of these two voltages, because they're a phase apart, is 180 degrees total. They cancel each other. They look like a short circuit. We get 0 volts. I got some interesting observations. Let me go back to the circuit and talk about these things. It might be a little easier to see. Let's go back to the previous page. When the frequency is very low, as we're approaching DC, the impedance of this inductor is j omega L. It gets smaller and smaller and smaller. So it looks like a short circuit in the limit as we go to 0. The capacitor is 1 over j omega C. As omega decreases, we begin to approach an open circuit. That was really what we talked about for DC circuits back in chapter 5. That an inductor in steady state looks like a short circuit, and a capacitor looks like an open circuit. To the other extreme, change in frequency. Suppose you go very, very high in frequency. As the frequency gets larger and larger, this impedance gets larger and larger in magnitude. This one gets smaller and smaller. So as we approach higher and higher frequencies, we could say infinity, that this becomes an open circuit, and this becomes a short circuit. Now in the previous case, because we had one that was a short and was an open, the impedance looking in here is going to be R plus infinity. Likewise, as the frequency gets larger and larger, as we approach an infinite frequency, this becomes an open circuit, this becomes a short, and again, the series combination becomes a very large resistance. But at the one frequency called resonance, which is 1 over the square root of LC divided by 2 pi, these two have equal and opposite voltages, so they act like a short circuit, and all you see is the resistance R. This is graphed on the last page. So in a design sense, we could think of a series resonant circuit that below resonance, it looks like an open circuit, very high impedance. Likewise, above resonance, it looks like an open circuit. It roughly looks like a resistance at resonance. These are some of the properties of a series resonant circuit.